So before I begin this series on hyperbolic trigonometry, I would recommend a pre-calculus level of background knowledge in math. You'll still be able to get something out of the series if you're not necessarily at that level, but I would recommend it being there just because there's some concepts I'm going to assume knowledge of that you might not be familiar with. But I still hope you stay tuned and get something out of the video. So let's get into it. Hyperbolic trigonometry. So we're familiar with the 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. But here you see we have some very different looking functions. Well, except for the fact that there's 6 of them and their names look somewhat similar, which is true. The trig functions, the traditional trig functions, are based on ratios of side lengths and right triangles. This is not the case for the hyperbolic trig functions. As you can see here, they're actually based on the number e, and this is all because of a deep relationship between the number e and the trig functions. I'll definitely cover that in a later video. But all I'm going to cover for today are the 6 trig functions and their graphs, some things they have in common. To start, I'm just going to go over the 6 functions. So you can see here sine, the hyperbolic sine of x, written S-I-N-H-X. The h on the end of them just indicates that it's the hyperbolic version of the trig function. So that's e to the x minus e to the negative x over 2. So half of the difference of e to the x and e to the negative x. The hyperbolic cosine is almost exactly the same, except it has a plus instead of a minus. And then just like the traditional trig functions, you can see on the bottom right there that all of the functions are derived from the other 4 functions are derived from the other 2 in the exact same way. So the hyperbolic tangent is the hyperbolic sine over the hyperbolic cosine. So that means you have e to the x minus e to the negative x over 2, all of that over e to the x plus e to the negative x over 2. But the 2's will cancel, so you'll have the fraction we have here, e to the x minus e to the negative x over e to the x plus e to the negative x. And then the hyperbolic cotangent, I'm just going to skip around there to hyperbolic cotangent. It's the cosine over the sine, or just the reciprocal of the hyperbolic tangent, so you could just flip that fraction and get that. Same thing with the hyperbolic cosecant and hyperbolic secant. You just flip the fractions for the hyperbolic sine and cosine to get those values. All of the identities, the trig identities I'm referring to, all of the trigonometric identities that you may be familiar with, they are all the same except for some sign changes, but all the numerical values remain the same for these hyperbolic functions. The signs may change, and that goes for your Pythagorean identity. I know that one has a different, that one does have a different sign, but your sum identities, difference identities, even the derivatives are all the same, just with some sign changes in some places. And I do want to make it clear that each of these 6 are functions of x. For any constant, for any number x, for example, the hyperbolic sine is e the natural exponential base e to the power of that number x minus the same natural exponential base e to the negative, or the additive inverse, the same number x, all that divided by 2. So just like the original trig functions, these are all functions of x. So thus they can be graphed in the xy plane. If you're not familiar with the number e, it's an irrational number approximately equal to 2.7. It originates from a very certain property it has in calculus. So all of these functions are based on e to the power of whatever number you're using. So these are all functions. And speaking of graphs, I am going to now move on to what the graphs look like. Okay, so before I close out, I just wanted to talk about the graphs of each of the 6 hyperbolic trig functions. So we'll start here with the hyperbolic sine. I think it looks kind of similar to the x cubed graph, where it has a bit of the serpentine shape. However, it's definitely a lot smoother than the x cubed graph. It kind of almost becomes like a nice straight line here in the center. Another important feature of this applies to all graphs, but you can especially see it here with the hyperbolic sign, is that um, it's comprised of e to the x and negative e to the negative x. It's e to the x minus e to the negative x all over 2. So these are two of its component graphs. You can see it slides smoothly in between them here for its entire domain. But what you'll also notice if you zoom out far enough, its end behavior almost makes it become identical to each of its component graphs on either end of infinity. And again, this is true for all graphs, but you can especially see it here. Its end behavior makes it tend towards being identical to its component graphs. Next is the hyperbolic cosine. It makes this very, very parabolic shape. It comes down here to 0, 1, and then goes back up. It is not a quadratic parabola. It can only be represented as a quadratic parabola in terms of other exponential terms, kind of like e to the x or 2 to the x. And you can use it to skip certain steps in problems that would include that, where you'd have to convert those into quadratics. If you didn't get that, that's fine. I am going to cover that process in another episode in this series, so it's probably sometime this month yet. So that will definitely be covered. Back to what I was saying though about the component graphs and behavior. This graph is e to the x plus e to the negative x all over 2. You can split that fraction up to be e to the x over 2 and e to the negative x over 2. So you can see here almost immediately it begins to become identical to both of those graphs on either side of infinity. Another important feature is that since it is e to the x plus e to the negative x over 2, it is the average of e to the x and e to the negative x. So if I plot both of those, you'll notice at any point, like let's say x equals 2, the hyperbolic cosine at 2 is the average of e to the 2 and e to the negative 2. That is the definition of hyperbolic cosine. It is the average. The red curve is the average of the blue and green curves at every single point. Next is the hyperbolic tangent. You'll notice I think it looks a lot like the inverse tangent graph, except that its asymptotes are 1 and negative 1 as opposed to pi over 2 and negative pi over 2. You can see that here. Y equals 1 and y equals negative 1. The hyperbolic cotangent has this very, it kind of looks like the 1 over x sort of shape. Here, I'll turn everything off. It sort of has that 1 over x type of shape where it, very hyperbolic there. It also shares the same asymptotes as the hyperbolic tangent. They are cofunctions, so it would make sense that they are going to have some distinct features in common. And lastly, we have the secant and cosecant. Now, the hyperbolic secant looks very different from all the other functions. It has the horizontal asymptote at y equals 0, comes up to 0, 1, and then goes on its way. Just looks like a little bump. It's a very weird graph, I think. Then you have your hyperbolic cosecant. It again kind of looks like the cotangent, where it's got that reciprocal like shape here, although I think it's a lot smoother than the cotangent. The cotangent's a little more abrupt. That's because of its asymptotes at 1 and negative 1 as opposed to 0, like the cosecant. And again, you'll notice that its asymptotes are the same as the secant function. So that's an interesting little thing there. So today I just kind of covered the 6 hyperbolic trigonometric functions, their definitions, how they're based on E, and then I showed off the graphs here. So next time, sort of in the same vein how the regular trig functions can be extended if you their definitions can be extended if you use the unit circle. These functions' definitions are extended when you use the unit hyperbola. It's another of the conic sections, hence the name hyperbolic trigonometry, actually. So that will be coming in 2 weeks. I hope to see you there. Thank you for watching.